So we stopped last time in the middle of the proof of the P-to-rail theorem. Let me remind you that we have a compact group G, and that the function f in L2 of G is said to be finite dimensional if the linear hull of its right shifts has finite dimension. And the theorem we were going to prove says that finite dimensional continuous functions form a dense subset of L2 of G, and this we proved. And also it claims that this subset is dense even in the space of continuous functions on the group G. So what we must prove now is the following claim. The set of finite dimensional continuous functions is dense in the space of all continuous functions on G. Which may seem to be non-trivial, because you remember that last time we proved the density of this set in L2 of G by using some Hilbert space tricks. In particular, the spectral theorem for compact self-adjoint operators was used for that. So this is something which is not available in the setting of this space. But still, we shall deduce this fact from what we proved last time, from the density in L2 of G, and this will be done more or less by convolving with an approximate identity. So again, I will repeat some portions of the technique required with the work required when we work with approximate identities, and it will be very similar. In principle, this is very similar to, quite similar to what we did in the commutative case. So I will not formulate general theorem. They're more or less the same, but simply I will repeat some arguments. Well, they are not involved in any case. So, so proof. Take some function k in C of G. This is a function to be approximated, and take epsilon positive. Well, first we use uniform continuity. There is a symmetric a neighborhood U of the unity in G. This is the unity of G in G. So that we have the following: K of S minus K of ST is dominated by epsilon over 2 for all S in G. So this is again a sort of uniform continuity, and I remind you that at the first lecture we proved an even much more general statement. And this is a consequence of that statement. Now, for this U, I remind you that U is symmetric, means that U to the power minus 1 is equal to U. Well, and to this U, we can apply Urison lemma and to find a non-negative, non-zero continuous function on the group G, so that also we can assume that we may assume that its norm in L1 is equal to 1. And moreover, H is 0 outside G. So this and this is the Urison lemma, and this. And this is simply normalization condition. We find some continuous functions satisfying this to these three, or even for these four conditions, then its L1 norm is non-zero because it is continuous and is not zero somewhere, so it is not zero on some open set and positive, so its L1 norm is non-zero. And after that, we simply normalize it, divide by its L1 norm to obtain such a function. Now also we may assume, without loss of generality, that H of S is equal to H of S to the power minus 1, because simply replace H by H of S plus H of S to the power minus 1 over 2, and we obtain what we need. So since U is symmetric, this is innocent to do so. Now it's more or less clear that the norm of the difference of K and TH of K in C of G is small. Even epsilon over 2 probably, something like that. I remind you what TH of K is. TH of K is the right convolution with H. So we used this operator last time. TH of K is equal to the integral over G, K of S. Let's write it this way. H of S t to the power minus 1, K of t dt. So this is this operator. We used it last time, and last time our H was even Hermitian, And I remind you that this operator, last time it was compact, and we used the spectral theorem for it. So consider this operator, and now I start to estimate this thing. So this is the supremum over S in our group, pointwise supremum of this thing. So K of S minus integral over G A of ST minus 1 K of T dt. And now it is standard simply. The measure here is a probability measure, so we can put this term under the integral sign because the integral of this function is equal to 1. And so before that, probably it should be done. The following should be done. Here in the integral, we make a change of variable. We replace t by st. Ts. This is possible because the measure is invariant. Now, when we do this, we what? T. K of Ts. So let the new variable u be equal to Ts. Then what do we have about t? T is equal to u to u s to the power minus 1. Okay, so we put it here. And we obtain t is us minus 1, so here it will be what? Something goes wrong. Something goes wrong. U to the power minus 1. Oh no. No. This way. So t is equal to us. This is a new variable. U is a new variable defined this way. Then, because of invariance of the measure, the integral will be in u, and here we have s times s to the power minus 1 times u to the power minus 1. So h of u to the power minus 1, and here k of us du. So this way it is better. and h of u to the power minus 1 is the same as h of u, because we have this. So we arrive at the supremum over S in G, the absolute value of the integral over G, and here it will be k of S minus k of US, h of u du. Okay. Okay. Well, and that's precisely what we need, because this function is supported on the neighborhood capital U, and on the neighborhood capital U we have this inequality. So we see that this guy is smaller than epsilon over 2. When we put the modulus under the integral sign, then this will be smaller than epsilon over 2. And here it will remain the integral of u over g, which is 1. So we have this estimate. Now this function k, thk approximates k, and why do we do so? The point is that we already know that we can approximate k by continuous finite dimensional functions as a metric of L2. And after that, we take that approximant and convolve it with h. You simply apply this th to that approximant. And then we shall, by this inequality, we shall get an approximation of k itself in the uniform metric. So let's follow this line of arguments. We proved last time that there is a function g, which is finite dimensional. And approximates our function k in L2 as close as we want. For example, we can demand that it will be with this precision. Our function h is even continuous, so it is clearly an L2, and its L2 norm is non-zero because it is non-zero on a set of positive measures. So everything is justified. We can approximate this k by g in L2, and we want an approximation in the uniform norm. But for this, we simply convolve this with h, apply th to this. I claim that th of whatever, say w, the norm of this, so the norm of this in C on G is dominated by the norm of h in L2 of G times the norm of W and L2 of G. This is the thing we proved in the commutative case, and in the non-commutative case, the proof is the same. Let's remind it. Simply, I repeat the arguments to be sure that non-commutativity doesn't make an abstraction here. So we have again th of w is equal to the integral over g h of s well, th of w as a point s as t to the power minus 1, w of t by the Haar measure. Now we must estimate this pointwise, so we take the moduli, and to this integral we simply apply the Cauchy inequality. Here with h I even may avoid writing the absolute value because h is non-negative. Now, by the invariance of the measure of the Haar measure, and by the fact that we are on a compact group, so it is unimodular, so the Haar measure composed with this inversion is the same Haar measure, we obtain what has been claimed. So this is nothing, none other than this norm of H in O2. So we have this, and after that we can write that the absolute value of th, or even so, th of k minus g is less than or equal to the norm of h in L2 of g, the norm of k minus g in L2 of g, and well, again we obtain epsilon. Probably it would be good to put here even 2 in the denominator. And now what? Now we see that combining these two inequalities, this one and this one, we see that the norm of k minus th of g in the space of continuous functions on G is less than epsilon. Sorry. Я слушаю.
Сергей,
Да.
извините, что отвлекаю. Я здесь сейчас вот в ПАМИ, вот в УВИКе,
Ага.
сказал, что у вас рассказ.
Ну, с понедельника, да. Сегодня можете заседать.
А вы думаете, как бы стоит рассуждать? Может быть, как минимум?
Ну, понимаете, значит, там, как бы это сказать, но ваш же докладчик как-то готов, да, правда, и значит...
У нас докладчик уже, он как бы отменил, он не приехал, у нас сегодня Смородина.
Ах, он не приехал, докладчик. Значит, приезжий докладчик не приехал. Ну, тогда я не знаю. Ну, смотрите сами. В общем, можете, на самом деле, особенно если там не очень много народу будет. Вот. Но сегодня он еще не действует пока, понимаете. Сегодня он еще не действует. Значит, так что сегодня можете заседать. Вот. Так, в принципе, то, понимаете, потихоньку, скажем, если немножко народу собирается, так можно и потом, но я не думаю, что это имеет какой-то смысл в этой ситуации, потому что вот будет... Нет, но риск небольшой, потому что, понимаете, значит, что тут, небольшой риск на самом деле. Потому что у нас... это тоже, да, лучше, конечно, им поменьше ездить, это верно, да, но вот... поговорите с Абдуловичем, да как хотите, на самом деле. То есть вы сегодня можете, понимаете, там сегодня это прекратится или в следующий раз, это большой разницы нету. Вот. Как-то.
Хорошо, понял.
Да, пожалуйста. I forgot to tell one important thing. Here, of course, this function is continuous for every function h, for every function w in L2, and we saw that last time because h is continuous. But it is interesting, precisely as it was in the commutative case, that even if h is simply an L2 function, then this thing is also continuous, and this is deduced from the continuity of the shift in the L2 norm, uniform continuity of the shift of the L2 norm, precisely in the way it was done in the commutative case. So in fact, we can write this without remembering what h is and what w is, simply two L2 functions, and their convolution will be continuous. So anyway, now we have this, and what do we need? So our function g was finely dimensional. Then this function approximates k uniformly. Well, if we prove that THG is also finely dimensional, then we are done. Because, well, I'll remind you what we needed to prove. We needed to prove this thing. How to do this? Okay, G is finely dimensional. Again, let's write this standard formula for dH of G at the point S. This is the integral over G H of S t to the power minus 1 G of t dt. And here we replace S by SU and T by TU. So when we replace T, nothing happens with the integration because of invariance, of the invariance of the Hauer measure. And when we replace this S by this, simply we obtain a shift, the shift of this function by U. What is the result? Well, so we see that THG at the point SU is equal to the integral over G of H of S t to the power minus 1 G of TU dt. Let's look here. S is replaced by SU, so we obtain SU here, and T is replaced by TU. When we invert, then we obtain U to the power minus 1, which is cancelled with this U, and this reduces to this thing, and here T is replaced by TU. So, okay. And what does this mean? This means that if we take th of g and shift it by u, then it is the same as if we apply th to the shift of gu. Well, and what must we prove? We must prove that these functions generate a finite dimensional subspace of the space of continuous functions. But we know that the shifts of G do generate a finite dimensional subspace. So let G u1 and so on G un be a basis in the space generated by all shifts GU. Well, then our function GU will be represented in this form. It expands with respect to this basis, and this formula shows us that THGU, we simply apply TH here, so it will be the sum over E from 1 to n alpha I over I from 1 to n alpha I TH of G UI, and we use this formula to see that this is the sum of the following functions. Okay, what does this mean? This means that every th of g u this way, every shift of this function gu is a linear combination of shifts of this of such shifts of these functions g. Well, if we take this function th of g, then every its shift is a linear combination of fixed finite collection of such shifts, and so this means that THG is finite dimensional. Okay, and the combination of all this finally proves the Peter-Weyl theorem. Now, last time I already mentioned representations, and now I want to discuss it in some more details. I don't want to stay in this theory for a very long time, so I want to explain only some very basic facts about what happens here. At least I want to show what the theorem we have proved means in terms of at least one representation, which is called principal representation. So what we mean by representation? Let G be a group, a unitary representation of G is a homomorphism of G to the group of unitary operators on a Hilbert space H. So phi of t t and phi of t1 t2 is equal to phi t1 phi of t2. Well, normally it is assumed that it should be weakly continuous. Or strongly. In the operator terms, this is called strongly. Let's always assumed that well, what phi of t alpha tends to phi of t in the strong operator topology. Whenever T alpha tends to T in G. So T alpha here is a net, of course, not necessarily an usual sequence. It may be a net and generalized sequence. Though the strong operator topology is a topology of pointwise convergence. So we require that the operators converge pointwise at every point of our Hilbert space. Well, this is a representation, and probably the main representation related with a group is a so-called left regular representation Well, in this case also people say that it is a representation on H. Simply to name explicitly the space H in which everything happens. Now, well, let's probably consider right regular representation. So here we assume that G is compact. This assumption is not required for the beginning of what I'm going to tell, but then it will be required because we're going to use the Peter-Weyl theorem at some point. So let's assume this from the outset. So G is compact, and phi of t, let it be, also I will denote this by ut, and ut of f is the simply the right shift of f by t. Well, and where does it happen? Everything of that. So this is surely on L2 of G. Simply take L2 of G, L2 again the Haar measure, as our basic Hilbert space, and in this space, our group acts by right shifts. Well, surely all these right shifts are unitary operators, and this basic property that this is a homomorphism it is clear, of course, in this case. Well, so this is the right representation. Now, when we deal with the representation, what we are basically interested in, it's invariance of spaces. So consider the general setting. Phi G B of H is a unitary representation. Unitary representation. A subspace H1 of H is said to be invariant, or phi invariant, if phi of t of H1 is included in H1 for every t in G. So this subspace is said to be invariant under the representation if it is invariant under all operators forming this representation. Okay, our aim is to decompose the space H into portions which are smaller but phi invariant, and with the hope that probably it will be easier to study this representation on invariant subspace because it is smaller, it is simpler to have them, and so on. Well, okay. So there is an obvious lemma. If H1 is invariant, then its orthogonal complement is also invariant. Okay, why so? Let y be orthogonal to H1. We take every x, an arbitrary x in H1, and take arbitrary t in our group G. Then phi of t to the power minus 1 x lies in H1, surely, because H1 is invariant. And what does it mean? It means that the scalar product, the inner product of this element with y is equal to 0. Well, but phi is a homomorphism, so so this is none other than phi of t to the power minus 1 xy, and phi of t is unitary, so its inverse coincides with its adjoint. So this is phi of t adjoint xy, and this is equal to x phi of t y. Okay, and this is equal to 0, and this is true for all x in H1. This means that if y is orthogonal to H1, then all these vectors are also orthogonal to H1, so we have proved this lemma. Well, okay. And next, let's define definition. A subspace H1 in H is said to be irreducible under phi, if H1 is invariant and H1 has no proper non-zero invariant subspaces. Proper means that it doesn't coincide with H1 itself. So the definition demands that our subspace should not contain smaller subspaces which are still invariant, that it cannot be reduced in such a way so that it remain invariant. And now theorem, let phi g b of h to b of h be a representation, a unitary representation then H is an orthogonal. Is there orthogonal sum? Sum of a collection H alpha of non-zero irreducible subspaces. Well, this is simply by the Zorn lemma, by a simple transient induction, proof. Consider the set of all collections F of subspaces of H with the following properties. First, all elements of F are mutually orthogonal. Second, if I take the union of F and take the orthogonal complement of it, I obtain 0. And third, all subspaces in F are non-zero. Every subspace in F does not reduce to 0 alone. Well, and finally fourth, all subspaces in F are invariant under our representation. Well, first, there exist such collections. One of them is the collection consisting of the only space H. So if we consider the collection of precisely one space H, then it satisfies these properties. Next, we order this set of collections we say that F1 is finer than F2 if each space F in the collection F1 is a subspace of some space in L2, in F2. So this is not the relation, and it's fairly easy to see that every chain in this partially ordered set of collection of spaces has a majorant. What happens here, how to find such a majorant? So if you have a chain Да, Коля? Ну, две совсем, я тут лекцию записываю, давайте говорите. Студентов нет все равно.
Я могу попозже.
Не, ну давайте быстро, если быстро, давайте, а что?
Вот у меня такой момент, мелкий вопрос. Дело в том, что меня Витя Михайлов просто попросил, поскольку он
ну, да.
Вот там, значит, титульный лист этот пришел по поводу...
Ну, так мы сделали его.
Сделали, хорошо уже. Все, тогда... То есть он отправлен, да?
Ну да, вроде, да, давно уже, я уже даже забыл.
Титульный лист по этой программе.
Да, я про это уже и забыл даже все. Хорошо, ладно, Коля. Угу.
Все тогда, Сергей
Ну, хорошо.
Хорошо, не отвлекаю больше.
Так, why? Mm-hmm. Why every chain has a immigrant, this should be obvious, but for some reason I don't see this immediately. Well, this should be obvious in any case.